Hello and welcome everyone to Getting Started with Apache Ignite, implementing a digital integration hub. We're going to help deliver a digital business platform. And as Venkat said, I'm a solution architect for GridGain systems. So for today's webinar, we're going to focus on the frameworks, architectures, and facilities that can be used to understand, organize, and deliver a modern digital business platform. We'll make this concrete with Apache Ignite and the facilities used to deploy Ignite as a digital integration hub. We'll also look at a couple of specific components that underpin the functioning of the digital integration hub. And we'll quickly look at some non-functional aspects of development, deployment, monitoring, and management. So if we start with the digital integration hub, let's investigate how it fits within a technical framework for digital business. Again, focused on the objective, which is for the digital integration hub to deliver a digital business platform. So how do we think the digital business platform, or at least the technical part of the platform, fit? Well, Gartner sees the typical businesses having 4 core organizations that each have their own needs for technical platforms. Customers with their customer experience platform, partners with their partner ecosystem platform, employees have their internal information systems, and things, as a catch-all for the IoT devices out there, they have their IoT platform. Now, at the nexus of these 4 platforms, or where these overlap, is the core central data and analytics platform. It's this central data and analytics platform that is the engine driving and running a business in the digital era. But Gartner's paper on the digital business technology framework explicitly excluded, among others, was data management and integration. Now, if you look at those 2 areas, that's where architectures can be useful in illustrating the inner workings and understanding the capabilities and constraints of that high-level framework. So when looking to implement the business or organizational specific technology platforms, Gartner lists the Digital Integration Hub, or DIH, as an architecture that works well for many of the organizations outlined above. When we look at the DIH, it has support for local storage or persistence, compute facilities to process events, and to crystallize services into presentation, business, or technical services, and integration facilities to ingest and egress data from external sources and targets. With all of this, an Ignite Digital Integration Hub supports multi-model, relational or NoSQL key value, multi-mode, and multi-consumer access and consumption patterns. Now, when depicting the DIH, you can draw it vertically like I've shown here, and that fits with Gartner's view of what an API and a digital integration hub looks like. But if we look at the bottom 2 layers, the integration and external sources, and we focus on that and split that or refactor it by separating the source systems from the target systems and the integration that goes along with that, we see that we get a more traditional data landscape of source systems on the left, generating data, flowing to subscribing components, and ultimately out to target systems on the right that might need to take advantage of the data and the calculations, the computations, the services that are part of that central DIH. In the center, we still have the storage, compute, and API layers to support app, tool, and composite service consumption. So now, the Digital Integration Hub is not the only architecture that would support the technical frameworks that Gartner laid out. A traditional enterprise data warehouse with operational data stores and dimensional data marts, maybe another architecture that you could use to develop this solution. There are other architectures making the rounds these days, like Smart Data Hub or Smart Operational Hub. One other alternative architecture is that of the event stream processor. And this better fits with those technical platforms that have fully moved to the real-time, message-oriented, event-driven paradigm as seen in this fairly complicated diagram. My apologies. Yeah, I'm not going to delve into this alternate architecture, but it is very compatible with the DIH. But it has a focus on more of the streaming aspects and messaging portion, facilities that you would need for that. And it's a good fit to describe and organize business technical platforms that are using real-time, message-oriented, event-driven paradigms like IoT. Back to the Digital Integration Hub, let's start with a particular use case. So if we look at the customer and employee organizations, they're involved in a common sales interaction. We have the sales to planning function. So this might translate to a customer's web ordering system, driving activity that affects inventory, which is then used for the demand and distribution planning, long-term sales, and production forecasting. If we put some pictures on here using some of the more common systems in these areas, we might pick Shopify for retail sales and SAP for production planning and forecasting. And we'd also need a central database for reporting and analytics for analytic tools like Tableau. Now, it's important to note that data flowing from sales to inventory is transactional OLT based, while typical analytics tools want dimensional OLAP databases. Now, this is where Ignite, with its in-memory platform and unified hybrid analytic transaction databases, supports both of those. So now, looking at an implementation of the Digital Integration Hub for that particular sales to ERP plus analytics use case, we see that Ignite provides the needed elements for this architecture. And what are those? Well, Ignite provides data ingest with the Ignite Data Streamer for ingesting data from source systems. There are other APIs, but I'm just going to talk about Data Streamer for now. There is the NoSQL and relational storage for both OLTP and OLAP data. And there's the event-based compute facilities, in this case, continuous queries, to trigger that logic based on the data ingest of and calling then business rules or services, and then data egress to outbound or target systems that are interested in what you have to offer. As we move from fitting a digital integration hub into a technical framework and its architectural characteristics, we want to look at the facilities that it needs to deliver that architecture. So again, seeing this horizontal digital integration hub diagram, we see the three core areas where Apache Ignite provides facilities. Storage, and Ignite is primarily known as a distributed in-memory data grid or in-memory database, but there's more to it than just storage. It has an ecosystem that provides a wide array of facilities to support data ingest and data egress from source to target systems. And in the DIH architecture, an important capability is performing compute for event handling in real time. So this is logic either directly attached to event data or encapsulated as services and APIs that can be called when events and the event data arrives into the platform. So let's review each of these in a little bit more detail. So starting with DIH storage and persistence, we see that Ignite supports both SQL and NoSQL key value APIs for data stored in its tables and caches. Now, generally I use tables and caches as synonyms, but there is a difference in that you do not need to apply SQL semantics to a cache. If you want it, you could just say it, but just keep in mind that there is no duplication of data, so they can be synonymous. The SQL or NoSQL storage is fully ACID transactional and provides the requisite isolation modes that you would want. Now, Ignite storage, these tables and caches, can be delivered in memory for the fastest overall performance. They can be in memory backed by a third-party persistence backend from external relational or NoSQL databases. And finally, it can be memory-centric with Ignite native persistence. Now, looking at the Ignite native persistence option, this is, as I said, memory-centric or memory-first option that also has disk-backed overflow and durability. It's support for multiple storage regions, delivering multi-tiered storage delivery, is fully transactional across all of those regions using a write-ahead log. And the complete API suite is functional across SQL and cache APIs. So you get read-through, write-through, query-through across all partitions, whether that data is in memory or only on disk. And a variant, I should say, of the cache store is also applicable to Ignite persistence, which supports loading data into the cache store. Sorry, into Ignite persistence. Now, on the other hand, third-party persistence option is implemented via an Ignite cache store class. These come delivered with Ignite for out-of-the-box implementations to popular SQL, relational, and NoSQL databases like Cassandra. It provides read-through for missing data and write-through for synchronization and cache preloading options. It's fully ACID transactional to the external persistence data stores. And just quickly, if you're trying to make out the lines in this picture, let me just give you a quick legend, an audible legend here. So the right two green and somewhat orange, maybe salmon colored lines, those are write operations in the cache API, and they use the cache store to write through to the backend data source and give you that transactional two-phase commit synchronization to the backend data store, so your data is kept in sync. The blue line coming from the cache API will read data from the cache, but if the cache, excuse me, if the cache doesn't have your entry, it will read through to the backend data store to get that entry for you. And then finally, on the lime green line on the far left under the load API, the load cache API asks the cache and its associated cache store to say, hey, go get the data and preload it into the cache so I have it available to me to serve up. Okay, so moving from storage facilities to integration facilities. Ignite includes a number of tools, APIs, and services that support or facilitate integration. For example, you can use Ignite's provided SQL line tool or any JDBC or ODBC tool like Talend or Informatica to ingest the data. You can also write an app using the key value or SQL APIs to add or ingest data via your application. However, in this webinar, we're going to focus on the Ignite data streamer and its API. Now, the Ignite data streamer provides buffered, multi-threaded writes, topology-aware dispatching to minimize your network I/O and memory impact. I should just remind the audience that Ignite is a highly distributed cluster. So being topology aware means that the data streamer can send the data to the right node to load and store the data in the right place. So that's why you get to minimize network I/O. There's no redirecting through some kind of proxy. It has extensible receiver logic, so when the data arrives on the node, it can do things to prepare the data for storage. It has at least once loading guarantees, so you know that the data will get at least once to your destination and be loaded. And while it does not support transaction semantics, you can have implicit and user-defined explicit transactionality if you want. However, be aware that there is no order guarantee because they may arrive at different nodes at different times. Okay, and again, this is the fastest load mechanism supporting both bulk and incremental feeds into your classroom. All right, moving from onto integration to compute, then let's talk about the compute that will focus on event handling and the interfaces that can call compute logic on real-time events. And there are three primary event-triggered facilities that Ignite provides that you would use in a digital integration hub. So the primary ones are the cache event or entry processors. And this is the processing that's associated to putting or updating data or an entry in a cache. There's cache interceptors, and this is a more feature-rich API to enable before and after callbacks for both gets, puts, and remove implications. And this interceptor, like its name sort of says, it has visibility to both pre and post change, and therefore can adjust or prevent actions from completing. And then continuous queries. This is the feature that we're going to talk about today. And this is a feature-rich facility that enables you to define an initial query to figure out what you want, what you're interested in, the remote filter to enable you to optionally decide whether you want the data to come back to you, to the local listener where the logic is stored. And there's support for remote transformation or remote transformer to allow you to have some logic so that the remote node can take the data, transform it before delivering it to you and your local listener. Okay, so if we look at what the event triggering facilities we just reviewed can call, there's a wide range of facilities. So when we're invoking this with a continuous query or a cache interceptor, these are the kinds of computes or things that can be called. Distributed closures, this is a broadcast or load balancing closure to execute across all of your nodes. Compute tasks, this enables you to do map, reduce, or fork join tasks in memory, co-located. And the affinity call and affinity run are co-located computations with the data in mind in the partition awareness. Machine learning and deep learning provides classification, regression, and clustering algorithms that can be called with partition awareness for massive scalability, and also support continuous learning with model updates, so you can train your model as new data comes in and goes through the system. And you can write business rules like using rules deployed as a distributed closure to enable complex business rules to develop using business audience generated rules. So if we move on to the implementation, a couple of these facilities, we're going to start with some of the data loading facilities. So as I mentioned before, and I'll just sort of quickly review here, for Ignite clusters and the in-memory database version that you would use for a digital integration hub in particular, we've got 4 core data loading or data ingest facilities, starting with the core Ignite cache API that includes puts and put alls with fine-grained synchronous and asynchronous data write semantics, transactional and order processing needs, plus SQL DML for those looking to use SQL, and optionally JDBC or ODBC tools and apps. This is perfect for applications with the highest integration demands for strongly consistent, real-time, incremental integration needs. Now, if you're moving from these fine-grained APIs to the Ignite data streamer, we get another set of APIs that turbocharge the Ignite data loading with the Ignite data streamer facility, providing the fastest data loading with all these features that I talked about before. Next, for caches and tables that have a cache store defined against it, remember we talked about third-party persistence backed by a relational or a NoSQL database. If you have one of these cache stores defined against your cache, then you can use the Ignite's cache's load cache method and implementation. And this is great for initial or bulk loading scenarios, and it also can be used for event-driven quasi-incremental loading, because you can pass parameters to your load method. And then finally, because Ignite supports common APIs, SQL, JDBC, ODBC, and those even support streaming, you can use third-party tools like SQLite, DB, or Talent, etc. You also, in the latest version of the JDBC driver, supports partition awareness. So you will get directed writes directly to the target nodes without any intranode data shuffle. So that's some great capabilities there. Excuse me. Okay, so that's a great, as I said, that's great for integrating with existing tooling, and there's no code involved for that if you're using those tools. Now, switching to the development process by which one would build an Ignite digital integration hub, the typical project looks like what's depicted here, with the cluster in red and black in the middle, and at the bottom right. Now, you would typically start by using the GridGain import wizard to introspect some existing assets you have in your environment. That would generate a Maven project using the web console generates, and soon the control center will also have that feature as well. With this Maven project, you would customize, build, deploy, and run this in or as a cluster in your environment. You would execute your data loading or ETL data ingest. And when that data is now in your cluster, you'd interact with it via your JDBC, ODBC, SQL tools, your Python application, your Spark application, etc. So that's the general process. However, if we look at the customizations in that step number 3 above, that's step 3 here, where you're doing that customization, where you're building it, you're adding your own logic. In that step 3, what would you do? Well, you would take that standard web console Ignite Maven project, you'd adjust the POM file, for instance, adding JDBC libraries, CSV parsing libraries, JSON libraries, JDBC, etc. You'd adjust the properties file name, I'm going to explain why, and the content for to externalize deployment parameters. You'd set business-specific class packages, and I'll show that in a little bit later. You'd remove the imported cache store, because again, we're moving to using Ignite native persistence. We're not going to use third-party cache store. We're going to create load and utility packages and create a class to load your CSV using the data streamer. And you might create, as we do in this example, some common utilities like a parse types utility class to handle the rules around parsing different data types and leverage that across your installation. Okay, so let's jump into that. So the Maven POM file here is what comes out of the box when you generate a Ignite project, and it defines the elements necessary to compile and build this Ignite cluster, this solution. And there are a number of techniques that can be used to streamline this usage, especially for handling versions. Here we're going to have 2 key elements that have been added. One, we're going to add a properties to define versions, and 2 additional libraries for, in this case, CSV processing and for JDBC data sources. Because in my example, I do both a CSV loader and a JDBC loader. Now, properties are great tools for externalizing the runtime parameters. Here are two examples, one for setting the JDBC connection parameters for your runtime environment. So you don't have that in your code. You have that in your deployment descriptor that your build tool would customize. And one, in this case, for setting the location for CSV files. So again, externalizing this from your project. The GridGain import database wizard organizes your imported cache and table models into a specific domain or package directory structure. Here it's com.gridgain.sales. By default, all the other components, the config, the startup, the load routines, are all placed at the root of the project. However, the problem with this is you're going to get class conflicts if you have multiple of these projects working together in the same cluster. So we move these artifacts under the model package so that it's organized together with your sales, in this case, packaging. Now, when using the import database wizard, it's going to build, as I said before, a cache store-based third-party persistence configuration. Because it said, well, you imported from a database, I want you to synchronize with it. Well, the only reason I imported in this case was because I'm actually I want the same model, and I want to maybe import from, but not because I'm storing it in this particular case. So while the cache store supports read, write, and load interfaces with the in-memory database or the digital integration hub, we don't want to synchronize. We're just going to load. So we're going to import those cache stores from the project in both the code and or the Spring Boot configs shown here on the left. Now, as I said before, for our data loading, there are many common tasks that we want to do. So we'll collect those in a simple utility class that avoids us having performance logic in many of the projects. You know, from one project to another, sale, HR, let's reuse that stuff. So for example, you may want to handle, when you're parsing, a value like a decimal. Well, a primitive can't be null. It has to be a particular value of a decimal. But you do want in your table to be null. So you may want to handle null handling in your parsing. So that's what some of these routines can do. You may want to handle how you handle dates, for example, as well. Okay, so now in terms of actually implementing the data streamer in code, let's walk through the one setup step you have to do, which is to create an Ignite ignition or instance of Ignite by starting it. And then we're going to have 3 steps for each table that you'll be loading into CSV. Okay, so first we're going to create a reader. In this case, we're going to do a file reader. If you're doing JSON, you might do a file reader with JSON. You might do a JDBC reader. So in this case, we're going to create a file reader, and we're going to use a CSV parser with some parameters on it. We're going to look at the object that we're loading to see what the key value structure is. It may be a primitive is the key, like an integer, but it might be a composite key, which is order and order line number. So we have to look at what the constructor is to understand what we're going to do with it. And then use the data we got from parsing our objects from CSV and create those necessary keys and values, and then feed it directly to the data streamer with the add data key value as I've shown here. Note, our file reader and Ignite streamer can work at maximum speed here because the streamer add method basically is asynchronous. This goes back to the lacking in transactionality and lacking in ordered sequencing, because this is essentially just going to give it data and let it do it at its own speed here. This is how we get the maximum performance. It also allows it to organize data to be sent to each particular node in a topology-aware, partition-aware approach. Okay, so that's an approach for loading data into the Digital Integration Hub. Moving on, a key part of the real-time event processing is handling that new data arrival. We're going to look at the continuous query facility and its ability to define interesting data, process that interesting data, and send it to services or to egress that data. So if we look at a diagram of the facilities available to Ignite for real-time processing, this diagram shows an Ignite client performing data loading, maybe like the example I just gave a few minutes ago. It might, however, it might use load APIs, it might use the put, SQL insert, etc., or as I said, the data streamer. We then have data handling facilities for when that data comes in. We talked about the cache entry processor, but I'm going to focus on two others right now. One is the cache interceptor, and that's a pre-load, pre-put, pre-insert handling or alteration of inbound data. And why would I want to use the cache interceptor? Well, think about duplicate detection. We may not want the data to be inserted or put, because on looking at it, we might see that there's an existing value there already, and the cache interceptor has the ability to get in the way of or filter out data that might not be of interest and call services or rules to check on that logic. You notice how in the diagram I sort of got it in front and interjected between the Ignite API and the actual cache, the table. The second facility on the sort of the right side of the cache or the table is the continuous query. And this is for handling business logic on the arrival of new data. So yes, the data is going to be inserted, but what do we want to do with this new data that arrives? So we think post-processing triggers, or with a selection and logic all bundled together. And what can I do once with either of these processes? Well, I can call compute services for handling logic associated to that. Now, if we look at a simple example, for instance, the order handling that we talked about in our use case, we see a continuous query deployed as a service attached to the order table. Data is then ingested by some tool or client or app. The continuous query, well, the data does get loaded into the table, yes, because it gets through the interceptor. Well, I think I've got these out of order, my apologies. The continuous query retrieves applicable rows, and I'll get back to what does an applicable row mean. And then logic is applied. For instance, hey, this order by this customer, let's update our analytic table, the customer 360 table, because we know we now have more orders from this customer. Maybe I want to do something with my customer 360 view. Okay, let's walk through this in a little bit more granular approach. There are essentially three phases that you go through to get this to actually work. So the first phase is the setup phase, and steps 1 through 3. So the first thing, and they're highlighted in little yellow stars here. The first phase, or first step, is for you to set the initial query and attach it to the cache or the table. This query is going to operate on all of the data nodes. So it's not a remote thing. It's attached directly to the node where the data exists. You also, in step number 2, have the ability to define a Boolean expression. So while the initial query says, hey, I want all sales transactions that are new, that might get you the fields of interest, but you may then want to filter out even further from that list other passing an additional expression or logic to suggest what you want to do with that before you actually pass back to the third thing, which is the local listener. So then you define your local listener, step number 3, and the logic, this specified logic will be invoked on any of the new data that is filtered, or that is new and passes the filter and is delivered to the local listener. There are options available here, as we talked about, in terms of calling compute, service, ML, rule, or any other Java function. So that's the first 3 setup steps. The second phase is the initial data handling, because you're creating your continuous query, but what happened prior to setting it up? Well, prior to setup, there may have been data in the system. So you execute the initial query, you handle that initial data, and then you optionally deal with that initial data. For instance, you might, send it to an outbound system, you might call a service, et cetera, et cetera. In this particular case, I just happen to have wired it on the screen as data egress. So the resulting processing of initial data, maybe that's interest to an external system. In this case, I send it out to an external system. So after we've handled the setup, we've handled the initial data, the initial query, returning all the data that was in the system prior to the continuous query being initially set up, we have our steady state operation. Okay, so in steady state, something is going to happen. A change in the external system is going to fire, and that's going to be impinged on or uploaded or sent to or API called or put to our table. That data will be on the Ignite table or cache, and it's going to fire this processing. First thing it will do in step number 8 is invoke, if applied, the remote filter, and it's going to evaluate if it's true, the data will pass. If it's false, we'll completely ignore that data. Once those entries are then delivered to the local listener, again, the local listener applies the processing logic that is applicable to this data. And in this particular case, I've called let's say an ML algorithm or a compute API service. In this case, step number 11, what I've chosen to do with this new data is to perform an internal update where the result of our steady state change data is to update an analytic table with information that might be of interest to this customer 360-degree view. So that's the 3 stages and 11 steps that is generated when we want to handle inbound data in an event real-time approach and being able to call services to do perform logic on the inbound data. Excuse me. All right, so let's get into the process by which one would actually code this. So I won't show you all the code because there's a few more lines than there were with the data streamer, but the steps are the following. You're going to define, so the continuous query needs a container or a process by which to run, to execute itself. So I have chosen, in this particular case, to use a service, a Ignite service. We can run the services can be deployed to multiple nodes, etc. So I'm going to define a query, a continuous query service, and it's going to have the interface, which is to start, stop, and adjust the filter on this service. We're then going to have a implementation of this query service for the order. So the order query service impl will in fact implement these 3 methods, and it will use the execute method to perform a stateful processing of those methods. And in there, it will, hopefully you can see this, or maybe take a screenshot or look at the PowerPoint after you deliver it. But in here, the important things here is, as I said before, we're going to set the initial query, which may be a scan query, a SQL query, text search query. That query, then we will define a local listener. What do we want to do when we receive the update? The order query, we can set a remote filter on it so that we can, if it returns a Boolean true, then we will process it. If it's false, we ignore it. And then we execute the query and go through the data. And we use a little bit of logic to look for whether we want to continue this query. So as you recall, I have a stop query method against the query service. So if I tell the service to stop, then the continuous query will stop and shut down. So that's kind of the approach, using a service, an Ignite service, to be the holder and runner of the continuous query, with continuous query performing the initial setup, the local listening, the filter, the execution, and then the shutdown when necessary. Okay. So if we put all this together with delivering a digital integration hub and putting that together into the technical framework for a digital business, we want to focus on how we deliver that. Let's think about the digital business platform and how we would go about developing that. Well, with Ignite, development is done with in Java, .NET, C#, or C++. Those you can use the entire complement, creating a cluster, nodes, servers, clients, full API in those 3 languages. The thin client API, which is pretty functional, but can't do storage, can be coded in Java, Python, C#, C++, Node.js, PHP, and others. And we have cluster and data import wizards to automatically generate cluster configurations for you, including Docker files if you want to deploy that way. So now, speaking of deployment, Ignite, the cluster, the servers, and clients can run in a JVM standalone or embedded in your own deployments, essentially on all operating systems. Virtually any operating system that can support a JVM, whether that be a mainframe ZOS, iSeries, all the way down to AMD, Spark, Intel, Xeon, all those kinds of platforms. It can be deployed through our Docker Hub-based Docker containers, which you can extend with your logic. And we've moved on to delivering Kubernetes with K8s-specific discovery and communication protocols. So setting up your interprocess communication in Kubernetes can be challenging, but we give you special facilities to do that, special protocols that know how to do that, and coming soon, operator-based configuration accelerators for you. Now, from a monitoring perspective, Ignite comes with command line, REST-based, and JAMX-based monitoring APIs. There are tools, both a GUI tool, Visor, web-based monitoring tools, the Web Console, and our new GridGain Control Center, which will work with Ignite and GridGain clusters. For monitoring, there is a brand new with 2.8.1 and with 8.7.23 and above GridGain. There's 200 plus new performance metrics to give you visibility to virtually any kind of operating characteristics of your cluster. And with the GridGain Community Edition and above, there's a new unified tracing facility to consolidate all your cluster activity into logical activities. So instead of having to now look through logs on 10 different nodes, now you can look at a unified log and get a single logical unit of work and recognize that that's been merged together with all the different nodes behavior, all the nodes activity together. So you can see all the activity for your transaction, as an example, as it respond and impacted 4 or 5 different nodes together. You see that together in a unified way. Very important for debugging. And then management and consumption. So the web-based cluster management tool can deliver you cache management, node and cluster baseline topology definitions, can help you set up your scheduling for and backup, your backup and restore processes, can set up alerts, alert sending out to people or to SMS, etc. Can handle your data center replication, etc. And the web-based tools also have SQL and cache metadata exploration and the ability to create multiple notebooks for a zero install data consumption platform. Just a couple quick slides here on the new control center, which really is a great tool for monitoring and managing and some consumption of Ignite. Again, this is sort of what it looks like. It's built, as I said, for 8.7 above, Apache Ignite 2.8 and above, and there's multiple versions. There's a cloud-hosted SaaS service. There's a downloadable developer version you can use for free, and then there's an on-premise version. Small is free, but anything more than 2 nodes, then that's a paid service. Cloud is free, by the way. Okay, and this is just a picture of what it looks like. So nice dashboarding, lots of metrics, interaction, and a great tool, feature fit for cluster management, like you want in a digital integration hub. Okay, in terms of summarizing what we talked about today, Apache Ignite and GridGain can be deployed as a digital integration hub, which will deliver a technical framework for digital organizations, again, out of sequence, providing all the core layers of an API system pattern for real-time exchange as you'd want in a digital integration hub. And it delivers storage for persisting your data in both OLTP and OLAP-based approaches, aka the new HTAP, hybrid transaction analytic processing, giving you real-time compute and event handling to build your business logic and services for your consumers, users, and systems, and has integration facilities to enable tools, services, and facilities to ingest and egress data from your data integration hub. So that's it. So if you had any questions during the presentation, or if you have any new questions, please feel free to work with that now. Venkat, I'll pass it over to you because I know you do that so well.
Let me start with one question about IBM that came in, Glenn. Can you comment on Ignite's integration with IBM? Specifically, the attendee wanted to know if the Ignite streamer has been tested with IBM mainframes, either in conjunction with other tools or just standalone.
It has been tested, yes. So the integration with ZOS was done past year, and the good news was it worked just virtually out of the box. There were a few things that needed to be done, and so this is where it might apply. So let me just talk to the general things that were tested. So all the APIs worked pretty much out of the box. There were a couple places where encoding had to be handled in the scripts, like the Start Ignite script. So that was relatively easily handled. There were a couple places where the endianness of the code had to be looked at, and those couple places were handled. So that's generally covers the things that make the mainframe different, the endianness and the encoding or the code page. So most of that is covered. Now, I will say, however, keeping in mind that in cases where you are creating the data, that you may need to deal with encoding yourself. So if you are doing specific things like reading the file system yourself, like if I was reading the CSV file or the COBOL copybook off of a vSAN file, it would be incumbent on me to read that appropriately. So as long as I've encoded it so that when the JVM runs, because our data streamer would be using the JVM, so when we run the reading of the file, as long as we know the correct encoding and we are the right endianness already, then that part is where the mistakes can occur. Everything after that will happen seamlessly to the back end, storing in the cache or the tables in the cluster or in the node, server node, inside the z/OS platform. Hopefully that answered that question.
Awesome. And another question from the same same attendee. What is the largest database size tested with GridGain? Do you have any statistics, such as number of nodes, memory used, number of concurrent transactions?
So there's a couple different measures there, and I don't know all of them, but I'll give you a couple that I do know. So one of our largest banks or financial services firms runs 2,000 nodes and has over 2 petabytes of data. Microsoft runs 650 nodes for their security. Now, they don't have as much data, but their transaction volume is multiple thousands of interactions or messages a second. Internally, we test with I think it's a 10 or a 20 terabyte data set, just for making sure that when we make changes, that performance stays where we need it. So those are some of the metrics that I know.
Awesome. Another question is from Sudhakara is, how does Ignite facilitate orphan records in an ingestion failure? How does the ingestion batch check for completeness of data sets?
Right, so that's a great question when you're dealing with data loading. So notionally, if you're using a import that does not have things like CRCs, redundancy checks, then you may need some other approach. So you may need a controlling flow, like a control flow that starts and stops the flow in between or surrounding your data load. There are, as I said before, because you have the ability to inject logic both during and after ingestion with the cache interceptors for things like orphan loss and continuous query for post loading processing. Those are areas where you can do different things, like for instance, orphan checking, duplicate detection, and then final record processing, which would then trigger maybe some scan to count rows loaded, etc. So that's it. There isn't something that you can just flip a switch to turn on, but the facilities around pre-processing, post-processing, and triggers would enable you to build some of that into your logic. Great question.
All right. So there was a couple of questions around comparison with other offerings, cache offerings like Redis. So how does Ignite differ from other platforms in the same space when it comes to the digital integration hub architecture?
Sure. So as I said, you could implement multiple architectures with Ignite, and multiple people or platforms could implement this pattern, this architecture. So Ignite is not the only one that could implement a digital integration hub. I would say if someone mentioned Redis, that you would not want to do that with Redis. So as good as Redis is, its focus is really on a cache and not on a strongly consistent platform. It's really about accelerating queries where you could deal with some data loss. So Ignite is, in the CAP theorem, is strongly consistent, highly available, and has a ton of resources for dealing with partition loss and avoiding that, or dealing with what happens if the partition were lost. So we're strongly consistent there, and that's a big part of when you run a platform like a digital integration hub. So yeah, I guess I can't necessarily say I've heard of others that are pushing their platform as a digital integration hub. Obviously, data warehousing is sort of an alternate approach for this. There are new terms like smart hubs, etc., that are out there. And so I think some of the key features that I would look for in this is that you got to support analytics, you've got to support transactions. And so those kind of drive some auxiliary features around strong atomic transactions, consistency across, highly available cluster. SQL queries should be something that you have. From an analytics perspective, the ability to have SQL is very important, right? And not just any SQL, but ANSI SQL, with the kinds of things that people like to do: inner joins, outer joins, select subqueries, sub-selects, et cetera, et cetera. So there's a lot of features that people expect, and so you could add stuff to your topology to add different things like caching. But if you want to deliver a digital integration hub, then you sort of need a platform that can do all of this stuff together.
Awesome. And maybe one last question. Can you comment on, the complexity of scaling? Like, how complex is it to bring up, a node, add a node, or sort of performance tuning and load balancing across nodes as you scale up?
Okay, so those are great questions, and there's two distinctly different answers. So the bringing up a node, adding more nodes, that's dead simple. Right? So as long as you have the same configuration, and you sometimes don't even need the same configuration, as long as the communication between nodes is visible, and whether you do that through our own multicast, whether you do that through a list of specific static IPs, whether you use Kubernetes for cluster node awareness, that small piece, as long as I can communicate to one node in the cluster, I can join the cluster. As soon as I join the cluster, I have complete visibility as a new node. I have complete visibility to all the caches, all the tables, all the logic, everything. I don't need to come to the table with anything. I inherit that by joining the topology. So if I already have added logic, added caches, added services to my cluster, I can add a new node with virtually zero intelligence other than just knowing how to communicate to it. Once I communicate to one node, because I don't need to communicate to all of them, if I can communicate to one of them, I then take on all the capabilities, all the caches, all the tables, all the services, all the features without needing to know anything. So it's dead simple to scale it for the needs you want. Now, tuning, on the other hand, is a much more subtle art to figuring out how to do this. So there are a number of things, a number of practices that we mentor and train people on. You can sort of think of it as much like a database plus awareness of where does the data reside in terms of node partitions across different nodes, like sharding, for instance. So knowing where your data is located and then delivering potential affinity between caches and tables so that you know that when a query is going to hit both the orders table and the order detail table, I want the entries for orders and for that same order details, I want those to be on the same node. I don't want them just randomly distributed because that'll make it harder on the cluster to bring them together. I have to go out over the network, bring them together, that's slower. So it's sort of database, everything that applies to a database applies here, plus knowledge of how the distribution and distributing the partitions across the network, how that affects your queries, your performance, etc. Don't have a lot of time, but that's kind of the thought process that I would describe.
All right. Thanks, Glenn. Thanks, everyone. Have a good day.
Thank you. Take care. Bye-bye.